Hi, everybody. I'm back. This is going to be part two, and we're going to start off with 0341, which has a low power complaint. It's on a 40-foot New Flyer bus with a Cummins engine and a ISC CAPS fuel system. And as it says on the screen, we have low power on acceleration. So first thing I do with any diagnostic is, I hook up the check codes. So I hook up the Cummins, and I select some parameters to start off on my test drive just to see what's going on. I look at ICV fault, which is injection control valve circuit fault status. I monitor battery voltage, and then I'm monitoring VCA actual and desired, which means I'm looking at the valve control angle of the injection pump. Okay, and I'm doing this because I want to see if there's any issues with these PIDs to help point me in the right direction. So when I get about halfway through the test drive, I notice on acceleration that the air conditioning just shuts off. And when I get back to the shop to review the data, its insights shut down and I don't have any data. So now I'm like, okay, what's going on? So I tried to reconnect and it still won't connect. I thought there was something wrong with my interface, so I tried another bus real quick and it worked fine on the other bus. So now I'm like, oh. So now I'm wondering, I'm putting it together, I'm thinking, okay, I'm not able to communicate with Scan Tool with Cummins. And I also noticed that the air conditioning shut off while going down the road. And I'm like, okay. So I know where this is going now, and when I get to the next slide, I'll explain why. So on these buses, the body is controlled by Allen Bradley PLC multiplex computers. Okay, and one of the features of the programming of the processor is if the battery voltage gets low, the PLC turns off the output for the air conditioning. And how it does that is it monitors an RPM signal off the back of the alternator. Okay, and the bus computer is looking for half of the output charging voltage. So if you're putting out 27, 0.3 volts, then it should be half of that. So around, like 13.5, 13.6. If you start getting below that, like 13, 12.9, 12.8, the bus computer doesn't like that, and what will happen is it will shut off the air conditioning system in order to conserve power for the entire coach. Okay, so the driver can get off to the side of the road, or hopefully they have enough battery voltage left that they can just drive it back to the shop and let us know about it. So after seeing all this, the next thing I opted to do was I wanted to test the alternator, check the ripple and the charging. And in order to check AC ripple, you have to have a scope. So here's my evidence here. And just let me get my pointer out. So if you look here, channel A is my battery voltage, channel B is my alternator voltage, channel C is my AC ripple, and channel D is the charge current going into the battery. Also, if you notice, see how long of a screen I got here? I'm over 16 minutes. It'll go even longer than that. This scope is amazing. So anyway, notice all the noise on these signals. That's not good at all. We have a problem here. So I see noise in the signal. I also see, if you look at the voltage, the alternator isn't charging, and the alternator is putting voltage spikes into the system. So here's a zoomed in capture just to show you a little bit better. On channel A, the battery voltage, it's dipping down to 7.933 volts, and then at a peak it gets to 35.27. My alternator voltage it's giving me a spike of 47.93 volts, and then it's going negative 11.2, and then my ripple is through the roof. I'm like 28 volts there on that spike, and 39.15 volts on the negative spike. So the alternator is not charging, and it's also putting excessive noise into the system. And the other reason why I was putting all that noise in is the bearings on the alternator went bad. I went up to it and listened to it while I was doing the scope capture, and like, man, that doesn't sound good at all. The bearings were bad. It was causing all this noise in the system with the bearings. So let's go to the next slide here. And this is just basically saying what I said before. The air conditioning's intermittently working because of this. It also proves that the reason why Insight was shutting down and booting me out was because of the voltage spikes. The computers don't like low voltage and spikes, and the fix for this vehicle was a brand new alternator. Now, the question is, could you have isolated the cause without a scope on this one? Yeah, you could have verified it wasn't charging with a DVOM, but would you be able to pinpoint the cause of Insight shutting down? So you would kind of like be asking yourself, okay, I'm pretty sure it's the alternator, but not 100% sure. So basically, you're rolling the diagnostic dice and taking a chance, and I don't like doing that. I like proof. I'd like to be able to confirm my repair. So here's the brand new alternator, and if you notice here, all the huge spikes are gone. It's nice and clean. The alternator's charging. I'm at 2712. The battery, the alternator's putting out 28. The batteries are at 2712. Charge current going into the batteries. I'm checking that because I want to make sure that those batteries are not bad and going to fry my brand new alternator. And the reason why is because when batteries get severely discharged, they turn into more of a load than a power supply. So as their potential difference goes down, they turn into more of a load. They draw more current. They demand more current. Okay, so the alternator is going to be working overtime, trying to charge up them batteries, because it also sees a drop in voltage, and it overloads the alternator because of the extra current and the extra heat. The extra heat overheats your rectifying diodes in your alternator. So when you do an alternator replacement, you always want to check your batteries and make sure they're good before you send it out the door, because if you don't, chances are it'll be back and you'll be putting another alternator on it and then wondering why the last alternator went bad. That's the reason why a lot of time alternators go bad. Okay? All because they didn't check the batteries. It's very important you do that. And here is a zoomed in picture of the AC ripple on this bus. This is an AC Delco DN50 24 volt alternator. It's brand new out of the box, and the peak to peak AC ripple is 351.7 millivolts. So all you HD guys and gals out there that work on this stuff, you probably know about the AC Delco DN50 24 volt alternator. It's out there all over the place in the HD world, and I just gave you a known good spec, so thanks. You can say thank you. So that's a known good. Alright, so we're done with that case study now. Here's the next one. This one was very interesting and a doozy all at the same time, and I think you'll enjoy it. Bus number 1191, 40-foot New Flyer hybrid bus with a Cummins ISL9 engine. The codes are 3582 SCR catalyst conversion efficiency data valid, but below normal operating range. Then I have a 3543 NOx limits exceeded due to insufficient regen quality. History, what's been done already. Both NOx sensors have been replaced. We've regened it before to try and remedy the issue. The after treatment history from Insight has been checked, and the differential pressure of the DPF filter is fine. We've also done checks to look for exhaust leaks, and none has been found. We replaced the doser. And then after that, we went on a test drive looking at data, and I couldn't see anything at all on Insight that gave me any direction whatsoever on how to tackle this problem, okay? And I'm not just using any run-of-the-mill scan tool, everyone. I'm using the factory tool. The factory tool couldn't help me, okay? So, after the test drive, I went back and I looked at the troubleshooting info, and it says on the troubleshooting info, you do a DEF pressure test with Insight to pressurize the DEF system and look for leaks of DEF. I'm like, okay, yeah, that's a good test. So I did that test, and I couldn't find any leaks. There were no leaks whatsoever. So after that, I did some research and looked at the wiring schematic, and I decided to hook up my picoscope to the control signal for the DEF pump, okay? And that's a voltage signal that is basically used to control the duty cycle of the pump current, okay? And I put a low amp clamp around the pump motor ground wire, and then I tapped into the DEF pressure sensor to look at its voltage, okay? So then I actuated the Cummins DEF pressure test again, and I found this. So right here, channel C, this is the control voltage to the DEF pump, okay? And basically how the circuit design is on this, the DEF controller, which is the computer, it sends out a voltage signal of 8.68 volts, okay? That voltage signal goes to the DEF pump, okay? So then it goes to the DEF pump, and then the DEF pump, the controller inside the pump, is grounding the circuit, okay? So it grounds the circuit, and depending on how much demand it has on the pressure, it will vary the duty cycle. So it's ground controlled, so the longer the ground is on, that means that the pressure will keep on going up, okay? Grounded longer, more current, pressure will rise more, okay? So it's duty cycled, and here on channel A is the pressure of the DEF pump, okay? Now if you notice how that when it starts to get up at the peak pressure, it's really hashy, okay? And notice that the pump current, it went up and then it dropped down, okay? So the pump current went up, and when that happened, it's building more pressure because it's the pump motor is squishing that fluid, and it's slowing the motor down, and that makes the current of the motor go up. And the opposite of that, when it starts to have pressure where it's dropping down, or your duty cycle is not grounded on as long, it makes the pressure drop, and it also makes your pump motor current go down, and it also makes the RPM of that pump increase, okay? So this is how it's controlled. the controller sends a voltage out, the DEF controller. The DEF pump then grounds the circuit, okay? And then the pressure sensor is the feedback signal, and that tells the DEF pump how much to ground the signal. If the pressure drops, it'll ground it more. If the pressure stabilizes, then it doesn't need to ground that signal as long. Okay, so I hope I explained that the best I could, but that's how this system operates. So let's go to the next slide. And here's something else I was talking about. I was talking about the duty cycle. Here's another, it's a really cool feature of Picoscope. It's the new duty cycle graphing. It's really cool. So if you notice here, like I said before, with the duty cycle, it's going straight across the screen. And then we have a change in duty cycle, though, during this pressure event, okay, during where I'm seeing all this hash, okay? So let's go to the next slide, and then I'll continue to explain. So we see a drop in the DEF pressure, okay? Pump current builds and drops off. With this, the pump RPM increases, and then we also see a black line going across the green channel in a percentage. What is that? And like I said, that's duty cycle. That's a feature of Picoscope that you can use to graph the duty cycle. All right, so duty cycle function, the Picoscope, it's pretty cool. I like it. It helps you find intermittent glitches and changes in the duty cycle on the scope. It helps you find the problems faster. It can also help you confirm system operation on duty cycle components. It can also help you verify what the computer software wants it at. So if the scope capture matches the computer, you have a reliable signal. So let's zoom in on that capture. And like I said before, the pump motor control is ground side controlled. Okay. So as this is on longer, the ground is on longer here. You see at the bottom, the duty cycle right here is higher because it's grounded longer. But once it starts taking away the ground, not as much, you notice my duty cycle is going down. My pump current also goes down, and then your pump RPM will increase, okay? And then my pressure is still hashy, but it's starting to level off now, okay? So what's the problem? We checked for DEF leaks, and the tank level was full. The computer's seeing a good pressure reading. The computer's able to control the pump duty cycle, so we know the circuit's working properly. Excuse me. So what could cause this momentary loss of pressure and make the pump RPM go up? Well, after looking at this for a while and scratching my head a little bit, in all honesty, trying to understand the controls of it, it dawned upon me of another variable on this DEF pump. Here's one of them right here. The filter was causing this issue. And I know what everyone's going to say, Mike, you got to be kidding me. It's true. The filter element had gotten all squishy, and basically what it was doing, it was causing a restriction, and then that was making the pressure go down just a little bit, get all hashy and stuff. And then you would also, you'd see your changes in, the duty cycle, and also in the pump motor current and your RPM. Okay. But here's another thing that I noticed about this capture, and here's the other variable that I want to talk about. The filter, was bad, and oh, I'm sorry, we need to go back. My bad. I wanted to go back. Let's see. Okay, so here's like one of the first captures. Sorry about that. If you notice here, my pump duty cycle is at 75%. That's on the initial turn on when it's building pressure and your current's going up and your pressure's building, okay? But we've got this hash, okay? Well, during normal system operation on a good capture, it'll do this same thing. It will build up the pressure, and then the duty cycle will then drop off, and then the pressure will just level off, but it won't have the hash on a good one, and the current will go down. Well, here's my logic behind that and what is happening. What's happening is it gets up to that preset pressure that the computer wants to see. It then says, okay, I'm at the proper pressure. I'm going to take away the duty cycle, and then I'm also going to divert some of that pressure through a divert valve, okay, that'll basically dump it back to return, okay, back to the tank, okay, and that's what's happening here. So I had good control. The pressure was building. It was noticing the pressure. The computer was noticing it, on the scan tool, its pressure. So it thought it was good. Okay, the computer thinks that everything is okie dokie. So it drops off duty cycle, and then it, in that process, when the duty cycle is lowered, then your current isn't going to be as high. And that's what's happening here, okay? So the only piece of data here that really put the nail in the coffin was the hash on the pressure signal. That was the one thing that stood out of the whole thing, okay? So that's it. But now, here, let me go back through here. And here is the a good capture, what a good capture is supposed to look like. Okay, so if you look on this one, I start the test. I have a 75% duty cycle going all the way across here. And then if you notice, pressure's building, pressure's building. I don't have any hash in the pressure now. It's good pressure and it's holding now, steady. Okay, but if you notice, I've got the same type of duty cycle signature, and the current is acting in a behavior the same way that the other capture was. Okay, so this is normal operation. It builds up to that pressure, it levels off, the computer senses that pressure, and then it takes away the duty cycle, and it stabilizes, okay? Because it doesn't need to work the pump as hard now, okay? So it just opens the divert valve, the current goes down because of that, and then it takes away the duty cycle, okay? So I thought that was kind of interesting. Originally, when I looked at this, I was thinking, opposite in the control of the duty cycle, but I had to, rethink it and look at it again because it wasn't making any sense. And that's another example of how looking at these signals with a scope can help you understand better what you're working on, okay? I just learned a lot by looking at that, didn't I? That is just awesome, okay? And here is a zoomed in capture, and this was of that known good. This was from a different bus. I'm sorry, I didn't have time to do the known good on the other one, but this is known good with no problems. And if you notice here, the pressure is staying steady. The current here is pretty much staying steady here, but also look at the duty cycle control. Remember I said the duty cycle is ground side controlled, and the controller, the DEF pump unit, the module in there is grounding it. And if you notice here at the bottom, right here, that's an increase in duty cycle. So it's keeping the pump on longer, and then duty cycle goes down, and then the width here of the duty cycle signal is less. Okay, so it's not grounding it as much. Okay, hope I didn't kill that too much, but I think it was important to understand that and my thought process. So so let's keep going here, and that's going to be it for this part. The next one's going to be on a 2013 New Flyer bus with intermittent operation of regenerative braking and surging. This one was pretty cool too. I had a fun time with this one, but we're going to leave that for the next part, and then we'll go from there. If anyone has any questions about anything that I've talked about, feel free to give me a shout and let me know. So anyway, hope everyone liked that, and I hope everyone has a good night.